Okay, what we're going to work on today is a test to compare two populations. We're going to compare two populations. So we have this group, and this group is, it has an x bar sub 1, it has a sigma sub 1, and here's another group, right? This is x bar sub 2, sigma sub 2, and we want to know if these guys are the same or if they are different. And so how do we do that? We're going to do a very simple test following our 10-step hypothesis process to get that done. But first, the question. A telecom company wants to know if there is a difference between cable and satellite subscribers. Cable versus satellite. We're going to take 50 of each. We're going to take 50 of each, and we're going to ask them to fill out a survey and rank that service from 1 to 10. Right? The cable subscribers are here, 50, and the satellite subscribers are here. This is our X bar, this is our sample average, and this is our sample sigma, or standard deviation. So let's get started through our 10-step hypothesis process, cable versus satellite. Step number 1, we need to do the hypothesis in English. We always start off with our alternative hypothesis. So what is our hypothesis? We want to know, we never write this as a question, but the question we're trying to ask is, are they different? But our hypothesis is never a question. Our hypothesis is the services are different. And the null hypothesis is the exact opposite. The two services are not different. Okay, that's good. Number 2. Step 2, we need to select the statistical measure. Well, we have a statistical measure. It is going to be the average, because we want to know if the population averages are different. Okay, so that's what we're going to measure. Number 3 is one-sided or two-sided. One-sided or two-sided. And here we ask the question, do we care if something is greater than or less than? If you want to do a quick normal distribution here to check it out, you probably can. And we want to see that mu is here. Do we care that it is greater than or less than? And you have to go back to the original question for this, right? We do, probably in the real world, we do care. But here, the subscribers doesn't care, right? We only want to know if they are different, right? Wants to know if there is a difference. Let me highlight that for you. If there is a difference. So we really we don't care if one's better than the other. We just care if they're different. That makes this a two-sided test. Number 4. Number 4 is hypothesis in math. So when we write this in math, again, we start with the alternative hypothesis, or hypothesis sub 1. And here we can kind of go up to look at our hypothesis in English. The services are different. Well, but we're not comparing the services. We're really comparing the mu, and then it's a two-sided test. So if it's a two-sided test, I'm pretty sure I'm going to use an equal sign. So I'm really asking if they're different. Is mu sub 1 equal to, but never the equal to in the alternative hypothesis, mu sub 2. Another way you can write this is to say mu sub 1 minus mu sub 2 is not equal to 0. If these two are the same, they subtract each other out, we get 0. This is kind of important. I think you'll see more often than not, you'll see this version of the hypothesis written out that way. The null hypothesis is the exact opposite. Mu sub 1 is equal to mu sub 2. And again, you'll see that mu sub 1 minus mu sub 2 is equal to 0. I think you're going to see these versions more often, because that's also the way we're going to cancel those out when we do our statistical calculation here in a minute. Number 5, alpha. Alpha is given. I don't think I wrote it down in the problem above, but alpha is going to be 0.05 for this particular example, or 5%. You might also see this as a confidence interval or a confidence level of 95%. You might see that. It's the same thing. Alpha is equal to 1 minus the confidence level, so we're good there. 6 is select a test statistic. Test stat. So this is a z versus a t versus chi-squared. What are we going to use? This is defining, here we want to define the distribution. Okay, and so we have a couple of questions to ask ourselves here. First, number 1, do we know if they are normally distributed? Normally distributed. There's nothing in the question that says that they are normally distributed, so I don't know. We assume that they're not. Number 2, do we know sigma? Do we know sigma? Well, if we go back to the question, we don't actually know sigma. Where's our list? Here's our list. We don't know sigma, right? What we know is a average for the sample and an average, and a sample standard deviation. This is not sigma. This is S, right? So we don't know sigma. Scroll, scroll, scroll. No, we don't know sigma. 3 is n greater than or equal to 30? And the answer is yes, right? N is equal, or n sub 1 is equal to 50, and n sub 2 is also equal to 50. So we have more than 30 observations for each. Because we said yes here, we know we're going to use a z distribution. So that's good to go. Number 7. All right, I think we're at critical values for number 7. Critical values. This is a great place to draw your distribution. All right, so in this case, we know we're normal, or we're approximating normal, to be very technical about it. We have a normal distribution that looks something like that. We have mu in the middle. This is going to be, this mu is equal to 0, right? This is going to be 0. We're going to go to alpha equals 0.05, but because this is two-tail, I'm going to have space here, and I'm going to have space here. So I really need to divide this by 2. That equals 0.025, and I know that I have 0.025 in the area under the curve in the left tail, and I have 0.025 in the area under the curve in the right tail. That leaves me with 95% in the middle, and that's where we get our confidence interval. So the question to us is, so the next thing we need to do is open up a table. Here is our z table. This is a positive z table. It is the right side of z. All right, and I'll make it a little bit bigger. It's over here. It's all the numbers that are on the right side of z, so they're positive as opposed to negative. I'll literally put it on the right side. Try to make it a little bigger for you. Here we go. Okay, and we know that we're aiming for 0.25. But since this table is on the right-hand side and the actual example on this table depicts the left-hand side, then we're really looking for 1 minus 0.025, right? And so this is a lot of stats 1 type stuff that you guys probably have done over there. So let's take a quick look at that. 1 minus 0.025 is equal to 0.9750. Is that right? That looks right. That looks right. So now we're looking for 9.750. And I like to just pick one column and walk down. This is as good as any. 0.90. Let me do it this way. I'll do it in white. 0.90. Now I'll do it in orange. 0.90, 0.91, 93, 94, 95, 96, 97. Okay, I'm close. 0.977. So I'm somewhere between here and here. And then I walk over, there's 0.9750. Sometimes you have to do whatever you think is the closest approximation, and that's okay. And then we walk this out to 1.9, and we walk this up to 0.06. I can combine this guy. You can't see that. So I'm bringing down. I combine this guy, and I get a z-stat, z sub 2 in this case, of 1.96. So if I go back up to the drawing I just made, I know that this value here, this z sub 2, is 1.96. And because this is symmetrical, I know that the other one is negative 1.96. You can work the one on the left, you can work the one on the right, it doesn't matter. 1.96 is our critical values. All right, let's redraw this. Let's redraw this table. The table, or let's draw this curve. Let me get a little bit more space here. Let's redraw this curve. Looks something like this. That is terrible. Let me do it again. Still not great, but whatever. And on the left-hand side, we have 0.0250. On the right tail, we have 0.0250. We know that this is a standard normal curve. So this is 0. We have identified that this value is going to be negative 1.96. We have identified that this value is going to be positive 1.96. We know that 95% confidence interval is in the middle, and we have 2 drops on the outside tail. So what do we do next? We define where we're going to make the decision. On the left-hand side, we're going to reject the null hypothesis. On the right-hand side, we're going to reject the null hypothesis. And in the middle, we are going to fail to reject the null hypothesis. Which, in effect, now brings us to step 7. No, 8. Step 8. We're in white. 8. 8. That's not white. 8. Which in effect brings us to step 8, which is calculate the stat. Calculate your test statistic, or compute, right, or whatever. All right. So the interesting thing about this is where we do have something that's a little bit different. Usually when we do a z-stat, we do x bar minus mu over sigma divided by the square root of n. But before we do that, I want you to think about converting this x bar minus mu over the square root of sigma squared over n, right? And so this is the same thing, but this is standard deviation, and this is variance, right? And so we're really doing the same thing in the denominator. These two are exactly the same, but there's a modification. And the reason I want you to think about this a little bit differently when we're doing our z calculation is that when we do two populations, or when we compare two populations, we have to think difference. We want to find the difference between two populations. We do the actual difference between them. So we're going to do x bar sub 1 minus x bar sub 2, this is its own little entity, minus mu sub 1 minus mu sub 2, this is its own little entity, all over the square root of sigma, that's not a sigma, sigma squared, or standard deviation squared, variance, sigma squared, variance sub 1 over n sub 1 minus sigma squared sub 2 over n sub 2. And if you just look at this computation, that can be a little intimidating, right? You've got all these numbers, you've got a square root, you've got these fractions. I mean, you've got a square root in the fraction, the denominators are weird, it can be very intimidating. But one of the things I highly suggest is to take a look at this as if you're doing a regular z calculation. This x bar takes the place of, or this difference calculation takes the place of the x bar, right? This one is this one, right? The mu takes the place of the mu, right? And the entire denominator is nothing more than the entire denominator here with the square root on the outside, right? This need not be different. So what are you doing? You're taking, you are taking the subtraction here, you are taking a subtraction here, you are taking a subtraction here, and then you're doing the regular z calculation. All right, this doesn't need to be super complicated. All right, let me rewrite it. Let me rewrite it because we're going to do some plug and play stuff. I don't want to do it in red. I don't want to be angry. There we go. X sub 1 minus x sub 2 minus mu sub 1 minus mu sub 2 all over the square root of sigma squared sub 1 over n sub 1. It seems tedious, but it need not be. Oh, my mistake. This is supposed to be a plus sign here. That is not a subtraction. That is an addition. Okay, I apologize for that. Plus sigma squared sub 2 over n sub 2. And now we do some plug and play stuff here, right? This doesn't need to be super complicated. And, wow, we've done a lot of work, haven't we? Where's our little chart? There's our little chart. Let me see if I can do it with this guy. Let me cut this out real quick. Control, that's not what I wanted. Oh, that didn't work. All right, we'll take the whole thing then. Control C. Let me zoom out. Let me bring it all back down here. Stay there. And paste this over here so that we have our, I just want this so I can see the variables. I just want to see the numbers. And then now we're going to do some plug and play stuff. X sub 1 is this guy here. So we're doing 8.8 minus 9.5. 9.5 minus mu. Now the thing about mu sub 1 and mu sub 2 is we don't know them. They're not in the problem. But that's okay, because if we're looking for, in our hypothesis, we're looking for the difference between these two, then we are testing to see whether these two are the same. And if these two are the same, then they cancel each other out, and this guy disappears, it turns into 0. Okay? No problem. And in the bottom, we're going to do, oh, I don't know why I did this in red. I don't want to do that in red. It's just scary if I do it in red. Sigma squared is going to be 3 squared over 50 because there's 50 observations. And now we have 2 squared over 50 because there's 50 observations there, right? If you calculate this out, you're going to take the difference. You're going to take the difference here, and then this turns into a 9. This turns into a 4. Luckily, these two are the same, so whatever. And through the magic of mathematics, we know that this is going to be negative 1.37. So our z, our test for the difference, is going to be negative 1.37. Whew, that seems like a lot. Let's come back to the chart that we've drawn back up here and figure out where am I going to put negative 1.37. Let's do this in blue. Negative 1.37 is obviously left of 0, and it looks like it's going to be right of 1.96. So 1.37 is going to be in here somewhere. Negative 1.37 easily inside our bands. So we are going to decide that we are going to fail to reject our null hypothesis. All right, let me go back down to the bottom. And now, number 10, state the conclusion. Do this in white for the sake of consistency. State the conclusion. My null was that the two services are the same. And my H sub 1 is that the two services are not the same, right? And so I'm going to fail to reject the null. Oh, can't do that. Fail to reject the null. We don't really reject that H sub 1, but we just kind of fail to reject it, so we accept that the two services are the same. More to the point, the real statement that we're making here is at 0.05 alpha, actually it's at 0.05 alpha, we cannot state that the services are different. And that's our conclusion. One note for the sake of consistency. When I wrote these hypotheses up top, I said the two services are not different as my null, h sub 0. And for my h sub 1, I said the two services are different. And so words are important, and I should have, while they mean the same thing and they translate the same way mathematically, make sure that you keep an eye on the manner in which you write these, because what you really want to do here, let me write the null. H sub 1 is equal to h sub 2, and mu sub 1 is not equal to mu sub 2. Because what you want to do is be able to translate are the same or are not the same, this little guy right here, into your equal signs. Okay, so just a note, you'll see that the ones I wrote in step 1 are different than the ones I wrote in step 10, but they mean the same thing. Just a point of clarification.